Organization of the Grassmann planes.
Okay. Thank you very much for the invitation. It's a true honor to be here. So nice to see you. Oh.
Yeah, sorry.
Oh, yeah,
Let's use that.
To help you. How does this work?
There's an on and off button on top of it.
It's just a little switch there.
Yeah.
Little switch. Ah, oh,
And then, yeah, click that.
oh, sorry.
Okay, that seems like it's on.
This is. We can hear. You can hear me? No, wait. I can do this. Okay, good. I can do it. Wow, this is fun. Anyways, okay, so thanks for the invitation. So the goal of today is to tell you what I know about Berkovich spaces and how I learned to love them. My training is in tropical geometry from the more Gröbner theory approach to it. And so this paper that we wrote jointly with Matthias Krevik and Annette Webber from Frankfurt was a way to get into this Berkovich world and learn about all the rich information it can give us. And despite what for me was some technical difficulties, how can I learn to bypass them and enjoy all of this powerful theory? So I wrote some references about this connection between tropical geometry and Berkovich spaces. The first one was this very, very nice paper by Matt Baker, Sam Payne, and John Rabinoff, when they basically describe all these analytic curves, the tropical curves, they relate the analytic curves to the tropical curves, they relate the metrics, and there's a lot of very, very nice results. The second paper is by Walter Hubler, Joe Rabinoff, and Annette Werner, who was, their aim was to generalize a lot of the nice theory that happens for curves to higher dimensional varieties, and sort of the inspiration that gave them confidence that a lot of the results that were expected to hold true were actually true was this nice example we computed. Some of our contribution was to give them the energy in the curves to say, okay, we have enough evidence, let's go for it and do it. So I'm going to tell you a little bit of what the ideas you can extract from our results to go and read their paper and see what's going on in a more abstract sense. And then finally, I wanted to advertise this nice paper about which gave an alternative proof of the same result, and they were clever enough to cut a lot of the hard combinatorics we were doing by using clever matroid language and using some torus actions to basically discuss, the things on a nice linear space, and then use this torus action to move the things that held in this linear space to the whole Grassmann. Okay, so there's very, very nice ideas in this paper, so I would recommend you to take a look at it. Okay, oops. So without further ado, let me get started by explaining you a little bit of the context of Berkovich spaces, and there's a little bit of difference between what Matthias said and my approach, so I'm going to repeat a little bit of the stuff just to highlight these differences. So let me start with the setup. So throughout the talk today, I'm going to fix K to be a non-Archimedean to complete non-Archimedean field equipped with an absolute value, and the absolute value is just a function from K to R non-negative that has the following properties. So the first property is that the only element that has norm 0 is the element 0 itself, so it gives you a nice, it's going to be a metric. Then it's going to be multiplicative, and then the third thing is going to be this non-Archimedean triangle inequality, or also known as ultrametric in some context, and it basically says the absolute value of the sum is bounded above by the max of the absolute value of A and the absolute value of B, and there's going to be an equality here if these two numbers are different. Okay? So the connection with that property here, it's something that happens for valuations. So given this non-Archimedean for absolute value, we can construct a valuation from K to R union infinity, which is a rank 1 valuation. Okay. Now let me advertise something. So this, everything I'm gonna discuss is coming from rank 1 valuations and elliptifications and tropicalizations in this case. And I believe Tyler, Foster, and Dhruva Raghunathan have an upcoming preprint on analytifications and tropicalizations of higher rank valuations. So I'm certainly excited to read this. So keep up the good work. Okay, so let me do some examples of this. So the first example is what happens if I have a trivial absolute value, then, which means everything that is not 0 has one for all x different from 0. In this case, every element is going to have the same absolute value. So any Cauchy sequence you can build off from here is going to be ultimately constant, so everything is going to be complete. Okay, so the completeness is given for free. So second thing, if you're into complex geometry and singularities, you like Laurent power series, we're going to be looking at the completion, which is the algebraic closure, which is the field of Puiseux series with the T valuation. And then, because we want things to be complete, I'm going to be doing completions. Okay? So, and thirdly, if you're into number theory, we can take the p-x, which is I'm going to take the closure of QP, and then I'm going to take its completion, and I'm going to take the p-adic norm. Okay? So in general, we can do this process. If I start with something that is complete, but it's not algebraic closed, I can take its closure, and there's a unique way of extending this absolute value, just as the case with valuations. And then I can take its completion, and the result is going to be complete and algebraically closed. So if you like algebraically closed fields, you can restrict to this case without losing much generality. Okay? The problem with this norms are they're very nice, but if you look at the topology that comes from this metric is really bad. So topology is going to be totally disconnected. So if you're interested in doing analysis, let's say, if you're interested in doing analysis over this field, then you're doomed to fail. You know? So the idea of Berkovich was to somehow, this space is bad, it's not, it's very bad from the topological perspective. So what he did was he designed a theory that added points to this space in order to fix this connectivity issues. Okay? So that's what I'm going to talk a little bit. I'm going to talk a little bit about this now, and then we're going to go back to tropical geometry and relate things as Matthias did using these log maps. Okay? So the idea of analytification in the sense of Berkovich is the following. I'm going to start with X to be a K-scheme of finite type. And I'm going to construct in a functorial fashion with a Gaga type functor. I'm going to construct a space together with a sheaf of analytic functions and as Matthias did in his talk, I'm going to disregard the sheaf for now because I'm mostly interested in connections between this topological space and tropical geometry. So the sheaves are going to be disregarded for now. So what's the idea? Well, the idea of this functor is going to be As with schemes, we're going to take an open cover. After an open cover, we're going to define this topological space, and then we're going to be able to glue them just as we did with schemes. So I'm going to define for you what I'm going to start with a finitely generated A algebra, and the Berkovich analytic space or the spectrum of this algebra is going to be very similar to the setting I did with absolute values. I'm going to have a function that takes points in A to R non-negative. It's going to be multiplicative as the previous one was. It's going to be a semi-norm, not a norm. And it's going to extend the absolute value on K. Okay? So what's this semi-norm thing mean? Well, it means that I can have elements that have take value 0 without being the element 0 itself. So this map can have a kernel. Okay? And then, as Matthias said, there's a topology of these spaces, and the topology I can pick is the weakest one, such that if I take any F element in my algebra, I can consider evaluation maps that take any semi-norm and I evaluate it at this element F, and these are all continuous. Okay? So that's the topology I put on this space, and as I said, we're going to be gluing these out of the affine patches. Let me say a little note. So what is the relation between K points in my original scheme and this analytic space? There's a very nice map to the analytic space that says every time locally I can describe a K point as a map from corresponding algebra to the field. And this map is going to give me a semi-norm on the corresponding analytification of this spectrum of this algebra. And the norm, the semi-norm is going to take an element F to, you can take them at F to an element at K, and then I have my norm K, so I can take the evaluation of the value of the element in K with respect to that norm. Okay? And this map is closed, is injective on closed points. So if you go to the algebraic closure, you get an injection. Okay? And this map is very well behaved if you have extensions of fields where the evaluations are respected. So if you have LK, a valued field extension, then you can form these sort of diagrams that are commutative. Okay, so everything is nicely compatible with taking extensions. Okay, so as Matthias, I think, told you in the pre-talk, this way of adding points is very, very powerful from the topological point of view. So the theorem that Berkovich proved in the 90s said that the space is locally compact. It's locally path connected. And then it says when this space has nice topological properties that come from nice algebraic properties from the scheme. So it's going to be connected if and only if the analytic space is path connected. It's going to be separated if and only if the analytic space is a Hausdorff space. It's going to be proper if and only if the analytic space is compact. And then finally, if I was starting from an absolute value that was non-trivial, then it showed that you'd look at the points over the algebraic closure, and then this is a dense set in the analytic space. So I'm going to be adding points to this, to the k bar points, and these points are going to be dense in the space. So I'm adding enough points, but I still have this dense set inside. Okay, this is all very nice, but it's a bit of a mouthful. So, as I told you, I was trained in the piecewise linear setting. So let me give you some connections with piecewise linear objects and examples. Okay? So if you want to construct examples of these spaces, let's think, for example, about maybe let me keep this definition up here. Let's keep this one in mind. Let me erase that part. So let's do some examples of multiplicative semi-norms over, say, polynomial rings. Okay, so let me describe for you the main example that we used in the paper. So it's this case of what we call the skeleton. So they're going to be semi-norms in principle, but the truth is that they're going to be norms, so there's going to be no kernel here. I'm going to describe for you some specific elements in the analytification of AN, and I think they're going to be induced by certain points in Rn bar, where here bar is R union minus infinity. Okay, so then, as I said, given a point, which I'm going to call rho in this Rn bar, I'm going to construct for you a multiplicative semi-norm over the polynomial ring. So I'm going to pick k of x1 up to xn. I'm going to give you a map that goes to R non-negative. And so what I'm going to do is as follows. So I'm going to have my nice polynomial ring written in this multiplicative form. So the sum is going to be finite. And I want to construct a map that has the desired properties. Okay? So the first thing I want to do is to extend the absolute value in k. So imagine I started with a constant. So if I didn't have x, I just had c to the alpha. Well, I better send that c to the alpha to absolute value of c to the alpha. It has to be multiplicative, so if I have a monomial like that, it has to be multiplicative, so it's going to be sending this to whatever I define here. I'm going to be describing this later, and it has to be satisfy this non-Archimedean inequality, which means I have to, the value on the sum is bounded by the max of the value, so the easiest way to build something that satisfies that is to just impose it, okay? So now I want to get something here that is non-negative real number, and if I have something in this R bar to the end, the easiest way to get something that satisfies that form is take the exponential of the inner product of alpha, and my rho. Okay, so that's going to satisfy, yeah.
So it seems like you have a lot of choices. Like instead of taking the max, you can take the min or the average. Like
right. So in this case, I'm doing max. So I want the absolute value is bounded by the max of the pieces.
Yeah, I know, but there are a lot of numbers that are less than the max, right? You can take
right. Yeah. This is a special one. This is why I call it the skeleton one.
So I guess I'm asking why you take the max as opposed to some other choice.
This is the one that is going to work. So. There might be, all the constructions I'm going to do are, well, essentially this is the one, it's a unique one that's going to satisfy something I'm interested in for the proof. But yeah, you can pick many things. In the same way Matthias was taking a norm and then he was raising it to some power, and there's a lot of stuff you can do. But, this one is the simplest one, let's say. Okay? Okay. So now let's see some of the piecewise linear things that appeared before. So Matthias already drew for you this picture. So let me do the case where I'm taking the affine line and I'm picking trivial absolute value or trivial valuation here. So I have to give you a point, a polynomial in one variable, and I want to construct for you this f. Okay, so if I write f as the sum of c k x to the k, from k starting from some element to another, and let's assume the beginning and end are non-zero numbers. So there's different values I can take. So if I'm imposing that the absolute value is bigger than 1, then all these elements are going to have different absolute value. And so what I told you about, the max is equal to the absolute value when there's no type, holds in this case. So then the one that has the highest power wins. If I take x to have smaller value than 1, then the reverse holds, and the lowest one is going to win. And the question is, what happens if there's a tie? Okay, then it's not clear what's going to happen, but what you can do is you can say, okay, let's think a little bit, and I'm going to define an ideal for you where everything has valuations smaller than 1. So we know since all of these guys have absolute value 1, then the norm on f is going to be bounded by 1 everywhere in this case. So this is a honest ideal. You can show it's a prime ideal because of this multiplicative condition. And since we're in a principal ideal domain, I can generate it with a single polynomial. And so then I can say, okay, f, I can write it, I can factor it in terms of g and an element that is coprime with g. And so then the norm of f is going to be the norm of g to the s, and the norm of h is going to be 1 because it's not in my prime ideal. So in this case, it says that the norm that I'm looking for is determined by two pieces of information. The first one is going to be the prime ideal. And the second one is going to be the value that I have for g, which is between 1 and 0. Okay? And here it's strict. So now you can recover the picture that Matthias drew for you.
What is the first element in this bucket?
It's this prime ideal p. So the valuation is going to...
This equivalence is the data needed?
The data needed in the third case to build this multiplicative similar norm. I need a prime ideal, which is going to tell me basically what the g is, and then the norm of the generator. And so then you can construct the same thing that Matthias did. So in the first case, we have when the absolute value of x is bigger than 1, and then I'm approximating this case, then the second case is, let's see if it should be this case. So if x is smaller than 1, you get this other piece. And then for any other prime, I'm going to have a branch that is, I'm going to have one branch per element in the spectrum or in my affine line. And if this one is generated by G, then the point in question is going to be determined by the precise value of G. Okay, so that each of one of the primes is going to give me a branch, and then I can know which point I'm talking about comes from a specific element between 0 and 1. And if I approximate the value of x, the absolute value of x to 1, I get the trivial absolute value. Okay, so that's the picture that Matthias drew. And you can see this color piece, which is a copy of 0 plus infinity, and you can take minus, let's say, or you can take log, and you can recover my R bar. Okay, so that that skeleton norm that I was talking about can be seen in this A1 as a colored picture. Okay, if I chose a different coordinate for my polynomial ring, then I would choose this piece and then a different branch of the same picture. Okay? So there's not a unique skeleton norm. It depends on the coordinates I give to my scheme. Okay? So this is what the affine line looks like in the trivial valuation case, trivially valued case. If you have non-trivial valuation, then you're going to see a similar picture where you replace this one branch point by a dense set of branches. If you have then, for example, a curve, then it's going to be locally modeled on these affine analytic spaces, but it's going to have some non-trivial topology that is governed by semi-stable models, or by a piecewise linear model, piecewise linear piece called its skeleton, and that comes from a semi-stable model. So let me give you an example. If I have an elliptic curve with multiplicative reduction, then you can degenerate the curve into a wheel of P1s over the special fiber. And so this picture is going to give you, the dual of this is going to give you a circle. And that's going to be my skeleton. And then I'm going to have a bunch of trees, infinitely many trees, infinitely branched, that I can deformation retract to my colored S1. So that's going to be my piecewise linear function, piecewise linear structure inside my analytic space. Okay? In higher dimensional cases, you can do the same thing. If you are given a semi-stable model for curves, we have that for free, but in general, we have to work a lot to do this. So that's one piecewise linear structure. Yes?
This picture corresponds to the deformation? Or
so
to
this,
the special fiber? Or
so this picture has a dual graph, and that dual graph is this blue circle. So you're going to have, of course, you're going to have a coordinates here. So every divisor, every P1 is going to give you a point, and then you're going to build edges according to how these things intersect.
Maybe the question was, on the left side you have a scheme,
yeah.
And on the right side that's the analytification, right?
Yeah, so what I'm saying is that if I have a semi-stable model, I can construct a piecewise linear structure inside my Berkovich space. So this is going to be the analytic, and the equivalent of this colorful line that I have here is going to be replaced by this blue circle. Okay? I'm just trying to give you a flavor of what things you can encounter when you study these spaces. Okay. So then the next thing that we learned from the previous talk was this nice tropicalization map that is going to be depending on an embedding. So my Berkovich spaces, these constructions are coordinate free, they're universal, but the skeletons are going to depend on some models or some embeddings or things like this. In the case of tropicalization, the very definition depends on a given embedding. So what I'm trying to say is the alternative piecewise linear structure. These are different tropicalizations. So again, as Matthias said, we're going to embed our variety. I'm going to embed it in a toric variety as a closed subset. And I'm going to assume that my embedding is such that the image meets the dense torus. And I'm going to put coordinates to the torus. So this is going to be spectrum of k x1, or y1 to yn. And then I'm going to define the analog of Matthias' logarithmic map, which instead of starting from the k points, it's going to start from this analytic space. It's going to be a map that depends on the embedding. So I'm going to send a norm, multiplicative semi-norm to, I have my coordinate functions, so I can evaluate the semi-norm at my coordinate functions. And then I can take logarithm here and get a number, and that's sort of the analog of what Matthias was doing, but I don't put a minus sign here because I like max, but that's the only difference. The image is going to be living inside certain copies of R bar to the n, which is going to be this tropicalization of my toric variety. And let me tell you in 3 cases what this picture is going to be. Essentially is the same as what Matthias told you. So if I have my variety to be Rn, then this tropicalization of my toric variety, it's this torus itself, then the variety is going to be Rn, because I'm basically taking evaluations. If I take affine space, then I'm going to get the same thing, except that now I'm allowed to take valuations of coordinates equal to 0, so I have to extend it by the minus infinity. And then if I like projective space, then I'm going to get similar thing. I'm going to look at points that come from the affine space. I'm not going to be allowed to have coordinates all equal to 0, so the point where all coordinates are equal to minus infinity is gone. And then I have some relation that tells me when 2 points in projective space are equivalent if they differ by multiple of non-zero scalar multiple, so I have to take that into account. And my evaluations turn multiplication into addition, so I have to quotient out by multiple of the L1 spectra. Okay? And now what I'm going to do is I'm going to define the tropicalization of x with respect to this embedding as an image of the tropical map. Okay? And this map that I drew was continuous. Okay? So this was a nice continuous map. So as I said before, a lot of these nice properties that my How do I spell this?
There's the right, the far right.
Far right.
Far right.
I'm sorry.
The third, yes.
I'm sorry.
PowerPoint talk.
What else can we do down?
So the nice result that Simon Payne proved in 2009 was that these combinatorial shadows of this analytic space under this tropical map are capture more information about the analytic space than what we think. So in principle, they're only a shadow, but the nice thing is that if I take enough embeddings into suitable toric varieties, I can recover my analytic space topologically by taking all these piecewise linear objects and taking the inverse image. So in the, I think I have this picture, but in the, so I can sort of approximate this crazy verge space by these finite piecewise linear objects. Okay?
What does that mean? How you are taking the limit over the embedding?
I'm
the embedding
taking.
varies how?
So the embeddings are as follows. So you're going to have a map into a certain toric variety. You're going to have a different map in a different toric variety. And you want to map, compatible maps in the sense that you have a torus here. You can map it to the torus here. And these maps are equivariant. So you can form these systems, and the way to go from one tropicalization to the other is by a linear map associated to a monomial map between the different tori. So you're sort of approximating, adding more and more and more branches to your space until you get the whole thing. But the catch is that it's not enough to go to a finite stage to capture the whole thing. If you want to capture a little piece of the Berkowitz space, there is a way of constructing the corresponding toric variety where you can see that little piece as tropicalization. Okay, but you have to cover the whole thing. You might need to go all the way to, well, you have to go to infinity. And so it was not clear how to generalize this construction about finding little pieces of skeletons of curves, as in this case, to higher dimensional cases. So what was the relation between these skeleta and these piecewise linear objects, embedded piecewise linear objects? It was sort of discussed in the curve case, but it was a bit open in higher dimensions, and so a lot of the work that Hubler, Rabinoff, and Werner did was to sort of give a way of extending these results on curves to higher dimensions. But the question that I was interested in is, if I'm not interested in going to the limit, but I want to find a continuous section, sigma, that goes from a given tropical variety to the corresponding analytic space, can I find this in a given example? Can I see my finite piecewise linear object inside my Berkowitz space as a closed subset? So that was the question we were interested in answering. So what we did was to discuss the first non-trivial example where this thing can be constructed. That is the case of the Riemann planes. So let me state the theorem, and I'll give you a little bit about how to prove such a result. So if that happens, as I said before, if this happens, so if so, we say the tropicalization is faithful. Okay, in the context of today's talk. So for me, this is what faithful tropicalization means. So the theorem that we prove was here Heidig and Werner is that the Blücher embedding of the Grassmannian of planes into projective space that sends a matrix 2 by n matrix to its list of 2 by 2 minors induces a faithful tropicalization. And the proof was really constructive. So we're going to start from a point in the tropical Grassmannian, and we're going to build a point in the analytic Grassmannian. So it was really, really constructive. And then one thing that June mentioned yesterday was that these piece plates in your object have some weights. Historically, the weights on the tropical variety was defined only as maximal cones, or maximal cells, excuse me. But we need the multiplicities on all points. So if I pick W point in the tropical image of the tropical variety, I can construct a multiplicity, which is a number which tells me the number of components on the initial degeneration with respect to W. And what we observed was that in our case, so for the Grassmannian, all multiplicities are equal to 1. Okay. And that was something that was observed in the curve case. If you have a case where a tropical curve has multiplicities 1, you can construct a section to the tropicalization map. And that was something that was expected in higher dimensions, but there were no examples to testify this result. So this gave an example of how to, why this evidence that this result should be true. So that's something that we proved. And then finally, the fact that there are multiplicities on points tells us something about the fibers of this tropicalization map. So
wait, number 2i is 5?
Number 2i is in general. So I'm saying that you can put weights on all points in your tropical variety. That's in general. Okay? And then I'm saying in our case, for this Grassmannian, given the Blücher embedding, we show that the multiplicities are 1.
The letter I, when you write trop xi.
Yeah, so in this case, it depends on, sorry. Is that better?
Yeah.
Okay. So the third thing was that this was also implicit in the work of Baker, Green, and Radenoff, that in general, if you have multiplicity equal to 1 for a point, then there is a distinguished point in the inverse image under the tropicalization map. Let me call that point gamma, and that point satisfies a maximality property, which means that if I have f, a point in, let's say, in the coordinate ring of let me take a patch where and W is in the Grassmannian, in the tropical Grassmannian, with respect to that embedding, and wij is different from minus infinity. So if I pick a point in that coordinate ring, then and I pick an element in the inverse image, then gamma is gonna, the value of gamma at f is gonna be any, the value of at f of any other semi-normative fiber. So it has this maximality property. Okay. And in general, so if you have more than one point, there's finitely many points that have this property, as many as the multiplicity. And so this would be the fact that we have one distinguished point that has this property. It tells us, okay, hey, why don't you pick this as your image of your section? So in fact, we can pick we can declare this special point as to be the image of our section, the point we're looking after, and that point is the one that works. So what Gubler, Berger, and Rabinov did is that they sort of highlight this property that if you have multiplicity 1, you can distinguish a point in the fiber, and that's the point that you want to be sending your tropical point. So the theorem that Gubler, Berger, and Rabinov proved last year is that if you have an embedding not on a torus, but on a not on a torus variety, but on a torus, has or gives, let's say, multiplicities equal to 1, then 3 gives a section. And I believe they're currently generalizing this to the case of toric varieties. What?
Next embedding in torus.
Sorry. In a torus. Thank you. Now, in the remaining of my talk, let me explain to you how one proves such a thing, or give you some ideas of why we chose to prove this for the Grassmannian and why it works. So the idea of the Grassmannian is that it was one of the first tropical objects that were studied beyond the curve case, and it served many, many purposes in, for example, construction of moduli of the pixels, giving compactification of M0 and M0n, using these tropical pieces. So as I said, we are given our embedding, and the image of this embedding is defined by the Blücher relations, which are Pij pkl minus Pik pjl plus Pil pjk, where I is less than j, less than k, less than l, and my coordinates of my projected space were given by P and j, and I was less than j. Okay. So the first ingredient in the proof was, okay, what is the tropicalization of this? This theorem by Speyer and Stonefeld from 2004 gave a very nice characterization of the space. They say, if I look at the points that come from the torus, so if I look at points inside modular diagonals, if I consider the points that where none of the Blücher coordinates vanish, and we define this as GR2N with respect to the given embedding. Then the tropicalization of this space is very nice from the combinatorial point of view. So we're going to be having only real points modulo the all one vector, and is the space of phylogenetic trees. Okay? So, so sorry. Okay. So what is the space of phylogenetic trees? I'm going to be encoding this space by two things. One is going to be a graph with no degree 2 vertices. It's going to have n leaves, and they're going to be labeled be a tree, meaning a graph with no cycles, and it's going to be labeled 1 through n bijectively. And then I'm going to have a weight, which is a map between the sense and gives a real number to the edges of my tree, and the weight of an edge is going to be non-zero if the edge is not adjacent to a leaf. Okay? So just to give you...
You said non-zero, and you all bigger.
Sorry, bigger than 0. Let me give you an example. So if I have n equals 3, what tree I'm going to be talking about is going to be a tree that looks like this. And the idea is that this space of trees is going to be a fan where each cone is going to be labeled by a tree as above, and I can tell you inclusions of one cone in another if the tree is one tree is a coarsening of the other tree, meaning I can obtain it by contracting edges. So for example, the cone that comes from the tree that has no internal edges is included in the tree that has an internal edge. Okay? So for example, if you look at Rachmaninoff 2-3, that's what it's going to look like combinatorially. So what I'm going to do is I have, this is what combinatorially this thing is going to look like. But if I have a point, a tree together with a weight, I can construct an element in Rn choose 2 by saying I'm going to take the distance between two leaves to be the sum of all the weights I encounter in the path from P to Q, and this point satisfies the tropical-Plucker relations, which is basically saying I'm going to take valuations of my ordinary Plucker relations, and it says the max, if I take xij plus xkl, xik plus xjl, and xil plus xjk is going to be attained twice, at least. So there's a tie. And so in this way, I can characterize points in my tropical variety as those that satisfy this 4-point condition. So now let me end by telling you how to construct this section, or what are we trying to do with this. How do the space of trees help us? And so the way it helps us is as follows. If I want to construct an elliptic Riemannian, I told you I needed to have an open cover. So I take the open cover given by putting back the affine open cover that we know. And I can realize this as spectrum of the following affine space. So it's spectrum of a polynomial ring with the precise number of variables. It's going to be isomorphic to, homeomorphic to an affine space. And here, the way to go from p coordinates to q coordinates, to u coordinates, sorry, is by dividing by Pij, and I know Pij is not 0. So I can restrict my tropicalization map to these affine pieces. And this is just the tropical Riemannian intersected with the points where the xij coordinate is different from minus infinity. And I can view it inside R bar to the n choose 2 by saying I send a point to, I'm going to pick the corresponding point where I fix xij to be equal to 0. Remember, there was a quotient by the all ones vector, so I can move things around by multiple of the all ones vector. So I'm picking the one where xij is going to be 0. Essentially, that's what I'm doing. And so, and this map sends this to log of the coordinates ukl for all kl that are different from ij, which is more than these coordinates I have here. So, so the idea to find a section is to say, I'm going to construct a section, let me put trop ij here, to trop sub ij that is continuous. And then the second thing I'm going to do is I'm going to show that we can, these sections agree on the overlaps of the different affine pieces, and so we can glue them. Okay, so let me tell you what goes wrong, and with this I'll end. What would be the naive choice? Well, I have my open space being an affine space, and I told you at the beginning of the talk that we have these skeletal norms. So what I can do is I pick the skeletal norms with respect to these coordinates. The problem is that this tropical map has more functions than those 2 and minus 4 coordinates, so I need to guarantee that my choice also satisfies that when I take log of those coordinates, I get the desired value. So remember, the skeletal norm was giving values to 2 and minus 2 coordinates, and I have more. So I need to ensure somehow that this is going to work. So the way we do it is, as I said, we guess that the value that I want to recover is this one, because I want that when I take the log of that, I have to get my x point back. And so this means that when I take log of sigma over point w at uik, I get the value I want, which is okay for kl in these coordinates, but I need to check that the result works for all the other coordinates I have on projected space, or this affine patch. So I have to use my Bruker relations. So this says that if I want to calculate the value here for this specific value, so if k is not in here, I have to express it in the coordinates I have, and then I have to use the definition of my skeletal norm, which says I have to take the maximum of the values over all these coordinates. So the value and its multiplicative, I have prescribed values on these coordinates, xil plus xjk minus 2xij. And this is the value that I want is xk minus xil. So I have a condition that tells me, here, that says xl plus xij is equal to the max, so I can sum 2 times xkm the coordinate on the other side, l and l plus xjk. And so this tells me that the x that I'm after is not going to lie in any cone I want, or in the closure of any cone I want, but it's going to lie in a specific one. It's the one corresponding to a single tree, which is called the caterpillar tree. So this naive construction only works for points that lie in the cone coming from the caterpillar tree. So the heart of the proof is to say, what if I have a different tree? So to finish with this, if I have, for example, the case of n equals 2, then I have to say the coordinates that I chose, jk, I have these 4 coordinates, il and jk, and this is not going to work because the max is attained at these 2 and it's strictly bigger than the max here, so I have to trade something. And so what I'm going to do is I'm going to trade this guy by ukl. So then I'm going to say ujk is going to be uyk to the minus 1 times ukl plus uyl ujk. And so I have to invert something. I have to trade something. And the idea is that there's some tricky combinatorics that are inspired by the curves and by the trees that tell you which coordinates I have to pick and what do I have to trade off by what. And the result is that this works. Okay, and with this I'm done. Thank you.